So now I want to get into doing some basic operations on vectors and matrices. So first, I want to talk a little bit about adding and subtracting. So adding and subtracting for vectors. Here, what we need to ensure is that our dimensionality is the same. And what do I mean by dimensionality? I mean that they're of the same size. So here, I have a vector that has 3 entries, so 3 rows and just 1 column. And I have the same thing for the second vector. It's 3 rows by 1 column. So now if I take the addition or subtraction of another vector, what I'm going to do is I'm just going to take the addition or subtraction of each corresponding element in each vector. So here, for example, what I'm going to do is take the top element, 73, and add to it 70 from the top element of the other vector. And when I take their sum, I'm going to get the 143. And now I can do that for each element in each vector. Now, for a matrix, how does it work? Well, if we, again, just think about a matrix as an extension of a vector, we can use the same intuition. We're just going to look at the same entry. So in row 1, column 1, we can subtract row 1, column 2, or column 1 in matrix number 2. So here, what I mean is that 73 minus 63. We're going to look at the corresponding entry in the matrix that it's being operated on. That's how we're going to continue for each entry of the matrix. So even in row number 3 in column number 2, 11 minus 8, and we're going to get 3. Now, if we want to multiply, so multiplying is going to get a little bit trickier. So to begin with, we can multiply by a scalar. Now this is actually going to be, instead of using multiple dimensional structures, if we're just looking at a scale, it will be straightforward. So what am I going to do now? Now, if I just have a scalar, it doesn't really matter that I'm going to have a correspondence of some dimensions. So what that means is I can just take a 3 or some scalar and multiply it by my structure. So 3 times this vector, well, I'm just going to multiply every element in the vector by 3. The same goes for a matrix. If I take some scalar and multiply that matrix by that scalar, well, I just apply that individual matrix or individual component-wise, element-wise multiplication, and I get my matrix product. Now, how does this actually look in practice if we're going to be multiplying by a scalar? Well, let's visualize again our vectors that we talked about earlier. Well, now if I apply a scalar to them, well, this is where you're going to see the name comes from. I'm just going to scale my vectors. So now, instead of going out 2 and 1 spaces, I'm going to instead go out 1 and 1/2 spaces. So you can see I've multiplied the light blue by 1/2, and I've gone less distance there. And for the orange arrow, now visualized in brown, has been scaled by 2. And so that's how it's going to look when we're going to be applying a scalar, a scale, to these vectors, these directions. Now, multiplying by a vector. So multiplying by a vector is going to be a little bit trickier. So we mentioned earlier that we need to have this concordance in the dimensionality of our structures. So before, when we were doing adding and subtraction, we needed that the rows and columns are the exact same. For us to do that, because we looked at the element-wise, the shared elements. Now, when we're looking at multiplication, things are going to be a little different. Now, we're going to have some direction in common, and that's going to be what we want to multiply, the dimension we're going to want to multiply across. So what does that mean? Well, right now, I've taken u, and u was originally a 3 by 1 vector, but now I've taken its transpose. So remember, I'm going to switch the rows and the columns. So here, u transpose corresponds to a 1 by 3 vector. V was also a 3 by 1 vector. So what do I mean by concordance? Well, now we have the 1 by 3 and the 3 by 1. Well, what I need to match is those inner numbers, so those 3's. So what this means is I'm going to go along the 3's. So the columns of my first matrix or the row of my first structure, and then the column of my second structure. So here I'm going to take the 2 and multiply it by the 73. That's how I'm going to get the 46. I'm going to take the 1 times the 165, and I'll get that. The 1/2 times the 10, and I'll get the 5. And so here you see that we've kind of just gone along. So we have my 1 by 3 and my 3 by 1, and we've just kind of matched these element-wise and taken their sum. Now this has a special name, and we're going to call this the inner product. And so kind of a mnemonic for you to remember that by is going to be the transpose. This t is in between these two vectors we're multiplying, in between inner product. It's going to be an easy thing for us to remember for our purposes. Now, what do I do now if I want to multiply the other way? So before I had a 1 by 3 and a 3 by 1. Well, now you can say, well, the 1s are also in common. What if I want to multiply along the 1s? So now I have a 3 by 1 times a 1 by 3. Well, here is going to be a little bit different. And so the way we're going to do this is we're going to look at the 2 and multiply the 2 by this whole vector, this whole row, and we're going to put it up here. And we're going to multiply this 1 by this whole vector and put it over here. And so how am I going to know what my ending structure should look like? What should the ending structure look like? So for u and v, u is a 3 by 1, and v transpose is 1 by 3. Well, if you remember above, we got a 1 by 1, a scalar, when we were doing 1 by 3 and 3 by 1. So what we can look at is the outside of this dimensionality. So ut is 1 by 3, vt is 3 by 1. The 1's on the outside, I'm going to get a 1 by 1 element. uv transpose, on the other hand, we have 3 by 1 and 1 by 3. So the matching is the 1s, but on the outside we still have the 3s. So we're going to end up with a 3 by 3 matrix. Now, going forward, we can kind of think about this. So what's a real-life example of doing this vector multiplication? Where would this make sense? Well, say I want to fit somebody for a wetsuit size, and I have their vector of their height and their weight and their shoe size. And I want to get an idea of what wetsuit are they going to fit into. And I know it should be some function. It should be related to people's height and weight and maybe their shoe size. So how can is there a way for me to go from these measurements to just one number, a wetsuit size? So what I'm going to do is I'm going to take my person vector, v, and I'm going to multiply it by u, this vector that's going to tell me, well, if you do this multiplication with some individual's measurements, you can get this scalar, and that's going to tell you about a wetsuit size. And so this idea also of going from this larger dimension, casting to a smaller dimension, so going from 3 by 3 to 3 by 1, is now going to be referred to as a projection. And so we've gone in a smaller dimensionality. And so now I want to extend this. So what happens if we multiply a matrix and a vector? So well, remember, matrices are just kind of an extension of a vector. So what can I do? Well, maybe I'm just going to treat this like I'm just doing this individually with individual vectors. So m, I'm going to look at each column as its own vector. So u transpose times the first column of m, well, I'm going to do what I did for the inner product before. I'm going to take the element-wise multiplication, and I'm going to sum all those values together to get 265. And now, how do I do this if the vector is on the other side? Well, now, again, I want these the dimensionality to match up. So I have a 3 by 2 and a 2 by 1. So that's good. That matches up. And if I have a 3 by 2 and a 2 by 1, what is the dimensionality of the final vector going to be? 3 by 1, exactly. So what am I going to do? I'm going to multiply 63 by 2, 58 by 1, sum it, and then it's going to go over there, my first entry. Same thing for the orange. I'm going to take my 135 times 2, and then my 110 times 1, and put in the second spot, and so forth. Now, moving on. So the last step for multiplying is now if we consider when we have two matrices. So how does this work? Well, again, we're just going to consider matrices as extensions of vectors. So like always, we're going to do our row by column multiplication. So we're going to go, that's always how we're going to be referring to our matrices as row, comma, column for our elements. So this, in this example, what we're going to do is we're going to take the first row, and we're going to multiply it by the first column. And that's going to give us our first entry in this matrix, our first row and first column entry here. So again, I have a 3 by 2 matrix, or a 2 by 3 matrix, times a 3 by 2 matrix. And again, the outer side, there we have a 2 along this direction and a 2 along this direction. We're going to get a 2 by 2 product at the end. So like we did before, we're going to take the 2 times 1 times 63, 1 times 135, 1/2 times 9, sum it, and get our entry over there. And we can do we can continue and do the same thing. So if I take the bottom row, now I'm going to fill the bottom entries of my matrix over here. And so my leftmost vector is going to get my leftmost entry in this matrix. Now, finally, if I want to do this again with larger dimensionality, I have a 3 by 2 and a 2 by 2. So what am I going to get? I'm going to get a 3 by 2 matrix product at the end. So I can continue and do the same thing. So 63 times 2 plus 58, I'm going to get 184. And I can continue and do the same thing where I have 63 times 0 or my 58 plus my 58 times 3 and fill in there. And that's about going to do it for our basic operations in vectors and matrices. So I just want to thank our sponsor again for funding this.